Okay. We are on the back side of our notes. At the top, there is a bunch of like definition-y type things that you can read and learn on your own. You all know how to read. I'm not going to read it all to you. However, I do want you to understand that there's more than one way to measure an angle. And up to this point, I think, in your life, all of your angles have been measured in degrees. Think about geometry. 30, 60, 90. That was degrees. Think about a straight angle is 180. That's degrees. You were measuring in degrees, and degrees are fine. But what you need to understand is degrees are completely arbitrary. Somebody at some point in time decided that they were going to measure angles by cutting a revolution up into 360 pieces. Okay, somebody could have decided we're going to cut it up into 400 pieces, right? I mean, it's just a made-up thing. The Egyptians were fascinated, and the Greek people were fascinated, the ancients, fascinated by 60s. That's why there's 60 minutes in an hour. They were fascinated by 12s. That's why there's 12 feet, or 12 inches in a foot. I mean, just all these are weird numbers that they were completely just fascinated by, and they set up their measurement system based on those numbers. But that's arbitrary. A radian, on the other hand, which is the measure of angles that we use in calculus class, is mathematically based. A radian is the measure of the angle determined by striking an arc of radius length. So a radian, the word itself is based on radius. A radian is the measure of the angle determined by striking an arc of radius length. So in other words, give me a circle, the most perfect shape of all, a circle, and its radius is, let's say 7. If I strike an arc on that circle that is 7 units long, do you see how that arc will create an angle? That is 1 radian. Okay? Now, you need to be able to change back and forth between degrees and radians, just like in chemistry. I don't know, you change between inches and centimeters or something. You need to be able to convert from one to the other. So to do that, I'm going to tell you that pi radians is 180 degrees. So in other words, half a revolution, 180 degrees, is the same as pi radians. So problem A is going to be a calculator problem. Let's get down to 3 for a second. We're going to do number 3 first, and then we'll come back up and do the calculator work. How many radians are in 90 degrees? So if pi radians are 180, then wouldn't 90 be pi over 2? So pi over 2 radians is the same as 90 degrees. So anything you would do with 90, you can do with pi over 2. How many degrees are in pi over 3 radians? Well, pi over 3 radians would be 60 degrees. Find the length of an arc. So here's a circle. Here's an arc. Right here, this is my arc. Intersected by a central angle of half a radian. So this is half a radian in a circle of radius 5. Now remember that in this circle, what would a whole radian be? How long would the arc be if it were a whole radian? 5. Because remember, a radian means the radius matches the arc. So I've only got half a radian, which means that arc isn't going to be 5, that arc is going to be 2.5. Exactly. In that reading at the top, they give you a little formula that relates arc length, radius, and radian measure. It says S equals theta R. I remember it as arc length equals radius times radians. Theta is a Greek letter. Trigonometry, remember Pythagoras and all those guys, all those Greek guys. So we use all these Greek letters for our trigonometry notation. It's just a variable. It's theta. This is the Greek letter theta, and it just represents an angle. Well, the angle has to be in radians if you're going to use this formula. So to remind myself, instead of memorizing this, I memorize this. So if I want to relate an arc length, a radius, and an angle, my angle has to be in radians. That's what this formula is. Okay? Now, they also give you a formula for if the angle is in degrees. Obviously, if they give you an angle in degrees, you aren't going to be able to use this formula. So they give you a formula for degrees, but it hinges on this relationship right here. Pi radians is 180 degrees. So x radians, or let's say theta, we'll say theta radians is x degrees. So pi radians is the same as 180. Some theta radians would be some number of x degrees. So if we want to know how x degrees are related, we'll take 180 theta and divide it by pi. Kids, I don't want to mess with that stuff. That's just too confusing for me. So I don't even worry about it. I use this formula for everything. Well, Mrs. Ford, that's great, but how do you handle a problem where the central angle is in degrees? So in other words, if I needed to find my arc length and the radius was 4, but the angle was 32 degrees, how would you do that, Mrs. Ford? Well, let me show you. This is this situation. The problem is that's degrees and I need it in radians, right? So I'm going to remember that little proportion, I is to 180, as something is to 32. Or you can come back up here, this relationship right here, and figure out, okay, if pi is 180, what's 32? Isn't that really what we're trying to figure out? For for me, it's easier to do it as a proportion. So x is 32 pi over 180. And I would just say, okay, my arc length is my radius times 32 pi over 180. And then I would just work out that arithmetic. Any angle can be changed from radians to degrees or degrees to radians by remembering this relationship. Pi radians is 180 degrees. So other radians are other degrees. This is 1, this is 1. Solve for x to make it 1. And then you can do any problem. Or you can learn that other formula. You need to be able to do a problem like this. So if you want to memorize that other formula they give you, that's fine. That is absolutely fine. All right, let's back up. I won't carry away with myself there. Oh wait, there's one more. Find the radian measure of a central angle that intercepts, find the measure of a central angle that intercepts an arc of length S in a circle of radius R. There it is, right? That's your formula. So how big's theta? If arc length equals radius times radians, then what does your angle equal? S over R. That's easy. Okay, we need to get through this calculator stuff and then we'll get on to some more fun stuff. All right, back to degrees. Degrees are subdivided into smaller parts. You know how a foot is broken up into inches? Or a meter is broken up into centimeters? Degrees can be broken up into smaller parts, and the smaller parts are called minutes. A degree can be broken up into 60 minutes. Just like an hour on the clock can be broken up into 60 minutes. So if you had something like 42.5 degrees, that would be 42 degrees, 42 whole degrees, and then another half a degree, which would be 30 minutes. And the minute mark is the little hash thing there. So this 42 degrees, 30 minutes is exactly the same as 42 and a half degrees, because there's 60 minutes in a degree. Just like there's 60 minutes in an hour. Well, the minutes can themselves be broken down into, you guessed it, 60 seconds. Now, why is that? Well, for us, drawing our little pictures on our paper, we really don't need those subdivisions. But if you think about navigators using angles to locate things, think about trying to find the, I don't know, the satellite that's up there somewhere. The Earth is huge. And so if you divide the Earth up into 360 pieces to get a degree, those pieces are going to be pretty big because the Earth is big. So then they break it down to minutes and break it down to seconds so that they can have smaller units to more carefully and accurately locate things. If you see something like 58 degrees, 11 minutes, and 24 seconds, that's how it's written. That's what it looks like. That's 58 whole degrees, 11 minutes, and 24 seconds. This means 24 sixtieths of a minute, and then that means 11 and whatever 60ths of a degree. When I took this class, that's how we had to figure this out. When it says convert it to DMS or convert it to degrees, we had to do it by 60ths. you got a button on your calculator, and that's what we're going to use. So, problem 1 says convert this decimal degree, so 37.425 degrees, that's a decimal degree. Would you agree that it could be written as minutes and seconds? It's a fraction of a degree, so we can break it into minutes and seconds. So here's what you do. You type 37.425, and then you have an angle button. It's above the apps button. You see where it says angle? So press second angle. And down in the list, you see DMS, which stands for degrees, minutes, seconds. So you go down there and press enter. And it tells you that that's 37 degrees, 25 minutes, and 30 seconds. So if you have a need for your decimal degree to be in minutes and seconds, that's the button you use, DMS. Easy as that. Now, what if we want to go the other way? What if we have an angle that's already in degrees, minutes, and seconds? And we would rather have it as a decimal degree. Okay, so now we're going the other way, okay? This one takes a little more button pushing. Start by putting in the 42, okay? Then go back to that angle menu, second angle, and the very first option is a degree. So go ahead and type that. So now on the screen it should say 42 degrees. Now type in 24. Go back into your angle menu, and right under the degree, do you see a minute mark? Type that. So now your screen looks like this. Now this is where things get hairy. Stay with me. Go ahead and type the 36. But in your angle menu, for some reason known only to the Texas Instruments engineers, they did not put a seconds. It is not in the angle menu. It is above your plus sign. Why is it there? No clue, but that's where it is. So alpha plus, oops, first you gotta put the number in. First you gotta put in 36, and then alpha plus, see how that pulls up the minute mark, and then press enter. So this angle, decimally, is 42.41. Honestly, these are fine exercises. We'll do some of this in pre-calculus, but once you leave this class, you are probably going to do everything in radians, which isn't degrees, minutes, seconds. So you're probably not going to have a lot of use for this beyond this class. But we do it in here. We have some more for that. All right, number 2. One of the big uses of trigonometry is in navigation. I mean, think about it for a second. Let's say a plane takes off from the airport, or a ship sets sail from port, and all of a sudden it crashes or it sinks or something, and you got to send somebody out there to get him. You have to know how far away he is and what angle, what course to send the rescue people, and that's all trigonometry. Draw a course of 155 degrees. Here's the compass. Everybody knows that a compass is north, south, east, west, right? Everybody knows that. On the compass, angles are measured differently than they are in any other trigonometry. So as we move through the unit, we are only going to label angles with this setup in a navigation problem. Here's how it's set up. Due north is 0. East is 90. south is 180 and west is 270. So angles are measured navigationally, starting from due north and measured clockwise. All other angles are measured way different than that, but navigation, this is the setup. So when they say, draw a course of 155 will look like this. Would you agree with me? That's 155 degrees. So when that ship sails on a course of 155 degrees, he is sailing in the southeast quadrant. And another way of indicating that, you can say a course of 155. That explains it completely. 155, there it is. You can also say south 25 degrees east. In other words, start out pointing due south and go 25 degrees to the east. Do you see how that would mean that same angle? So when it says write an alternative way of expressing, that's what it means. When we write them this way, for some reason, we always use north and south first. Okay, so we're not going to say east, however many degrees south. We're not going to do that. We're going to say south, 25 degrees east, or north, X degrees west, something like that. All right, so let's look at the next one. Where is 280? 280 degrees would be right here. Would you agree with that? So what would be an alternative way of writing 280 degrees? North?
-8.
No negative, no, north, 80 degrees west. George?
Can you just do west 10 degrees north?
We don't usually do that. If you said that to me, I would know exactly what you mean, but for some reason, when you see this like for real in real life, it's north and south first.
Are you always going to go clockwise?
Yes. In navigation, this is the setup always. Every time. You're talking about a ship sailing, a plane flying, you're going to do this as a setup every time. All right, so that takes care of that page. Okay, now let's get to the fun stuff. Find the perimeter of a 60-degree slice of a large pizza. Okay, talk about a real-life application. You buy a large 7-inch radius pizza. So here's my pizza, 7-inch radius. You cut a 60-degree slice out of it. And we want to know the perimeter. So, wouldn't the perimeter of the piece of pizza be that red thing? So I know for sure it's 14 plus something. This is an arc. Arc is radius times radians. The radius is 7. Please don't use 60 because that's a degree. Now it's an easy degree, so you might just be able to figure out how many radians that is. or you can do it with the proportion. Pi is to 180 as something is to 60. I know pi radians is 180 degrees. How many radians are 60 degrees? Well, did you think to yourself, pi over 3? Did you think that? If pi is a 180, then 60 would be a third of that. So your radius times radians is 7 times pi over 3, which is 7 pi over 3. There's the perimeter of that piece of pizza. That's called the exact perimeter. If you type that in and get a decimal, you're not exact anymore. All of our work will be exact unless I tell you otherwise. So we're just going to leave it right there like that. And the unit on that is inches. The running lanes at the Emory Sears track at Warfield College are 1 meter wide. The inside radius of lane 1 is 33 meters and the inside radius of lane 2 is 34 meters. How much longer is lane 2 than lane 1 around one turn? All right, so I'm going to go ahead and draw this picture as best I can. So this is the inside radius of lane 1, and it's 33. And then the inside radius of lane 2 is 34. How much longer is lane 2 than lane 1? Do you have track and field athletes in here? Yeah, it's why they stagger the 400, right? Because if you're in lane 2, you're going to run farther than the guy in lane 1. So your job is to figure out how much farther in this track right here. Any thought on that, how we might proceed?
Find the arc length.
Find the arc length. So for lane 1, we're going to assume the runner is running on the inside of the lane, right? So we're just going to find that distance right there. How will we do that? Just red. We're only looking at red right now.
That's like a 180 degree.
Well, we're talking about 180 degrees, which is pi radians. So the arc length will be the radius times the radian measure, which is pi radians, right? Is that okay with everybody? Yeah, I'm going by real picture. Okay, so 33 pi is lane 1. What will lane 2 be? 34 pi. So how many meters longer does the guy in lane 2 have to run than the guy in lane 1? Pi? 1 pi? Or about 3 meters more. Okay. Albert's truck has wheels 36 inches in diameter. 36 inches in diameter. If the wheels are rotating at 630 revolutions per minute, oh my gosh, we've done this before. Find the truck's speed in miles per hour. So we're going, remember doing these before? 630 revolutions per minute, revolutions per 1 minute. And we want to do something to that and eventually end up with miles per hour. What does this have to do with what we're talking about now? What's a revolution? A circumference. And isn't a circumference an arc length? It's the whole arc length. But we have a formula for that. We don't need this formula. What's circumference? 2 pi r. Now before you say anything, I want you to think about that. I promise. I'll stop after this problem, but I want you to think about this. Circumference is 2 pi r. Arc length is radius times radians. Radius is r, right? That's the same radius. If we're doing an entire arc, how big is that angle? 360. What's 360 in radians?
2
pi. That is your arc length formula if you're going 360 degrees, which is what a circumference is. See how it all fits together? Gosh, you gotta love it. Okay, so here we go. We gotta get from revolutions per minute to miles per hour. So we just got done talking about that a circumference is a revolution. So what's a circumference for this thing?
36 pi.
36 pi inches? 2 pi r, 36 pi inches. All right, so now I'm in inches per, wait, those are gone. So now I'm in inches per minute. All right, I gotta get to miles per hour. So what should I multiply now?
Feet. 12 inches and 1 foot.
12, let's see.
1 foot equals.
I got 1 foot, 12 inches. And then 5,280. Wait, I need to go the other way. 1 mile is 5,280 feet. So let me get straight here. So I got rid of inches, I got rid of feet. Now I have miles, I'm good. But I have miles per minute.
60 minutes.
So 60 minutes in 1 hour. And now I will have, whoops, yeah. Now I'll have miles per hour. Let's figure out what it is. How fast is Albert going?
67.47.
I got 67.47. Anybody else get that?
That's what I got.
Anybody not get that? Remember, when you type this in, guys, when you type it in, I would type in the whole numerator. So 630 times 36 pi times 60. Then divided by, then either put parentheses with everything, or what I do is divided by 12 equals, divided by 5,280 equals, because you gotta make sure you're dividing by both of those. So either put it in parentheses or do them as two separate divisions. Okay? Now, I promised I would do any more problems, but I do want to talk about number 7, the difference between statute miles and nautical miles. How many of you have ever heard somebody describe a speed as knots? Okay? Knots. First of all, knots is a speed. So like an airplane is flying at 400 knots or whatever, okay? That's a speed. Knots are nautical miles per hour. Okay? Nautical miles per hour. Your speedometer is not in knots. Your speedometer is in miles per hour. Those are statute miles. Does anybody know why there's a difference? Why are there two different things?
Is it because they move faster? No.
They don't necessarily move faster, because a ship, for example,
Yeah, they
the
move
ship's speed is
fast.
measured,
Okay.
they don't really move that fast. And their speed is measured in knots. If your vehicle is going to travel great distances, I want you to think about this for a second. If it's going to travel great distances, let's say your airplane is, here's the globe, your airplane is flying from New York to London. He's not going in a straight line, guys. He's not. Because he's following the curvature of the earth, isn't he? Now, when Lisa Ford drives from 7843 Teal Way to Cathedral High School, I'm going in a straight line. Because in terms of the earth, that distance is like minuscule. But when you're traveling great distances, you must take into account that you are traveling in an arc, not a straight line. So nautical miles take into account the curvature of the earth. Planes, space shuttles, ships, things that travel way long ways, they use nautical miles. Okay, aren't you glad you came today? You learned so many useful pieces of information today.